create a very high quality mesh, and also the mesh number should be sufficient or the high enough to get a very good result. So the two things, the sufficient number of the mesh and the quality of the mesh. For quality of the mesh, I yesterday talked about a certain property. Can anyone please tell what was that property?
তৈমুর ভাই,
জি, হ্যাঁ, বলো
রেকর্ডিং ভাই
স্বামী।
অন করা হয়েছে ভাই, আর ভাই ভাই স্লাইড বা কোনো কিছু দেখতেছি না ভাই, মানে
আমি স্লাইড হচ্ছে
আচ্ছা ঠিক আছে।
দেখাচ্ছি একটু পরে।
আচ্ছা
সো হোস্ট ডিসেবল পার্টিসিপেন্ট স্ক্রিন শেয়ারিং, একটু স্ক্রিন শেয়ারিংটা আমাকে এনেবল করে দিতে হবে সবাই। স্যার করা হয়েছে। ওকে, থ্যাংক ইউ। So this is that's what I was talking about. I yesterday mentioned about a particular topic, a particular term on which the mesh quality actually depends. So can anyone please recall what was the property?
Sir, skewness.
Yeah, skewness. Okay, thank you. Very good. What's your name, please?
Sir, Nuraldin.
Nuraldin. So you are in currently which level? Level 4 or level 3?
Level 3.
Level 3. Have you done any operation in ANSYS so far?
No, sir, but I've tried to tried a laminar flow simulation console previously.
In console?
Yes, sir.
Okay. Thank you. Thanks for your interest. And you can also try console. It's more advantageous, but in some cases, but actually for Fluent or the CFD, ANSYS is more popular. And thank you very much for your answer. I appreciate it. That this is actually skewness. That is actually the distortion of the cell from its original shape. So that's I mentioned that you need good quality mesh, and you need to have a sufficient number of mesh, and after that you have to have an idea about the grid independence test. You must know that whether your number of the grid or the cell is enough or not. So to do that, we actually have to run the simulation for some certain global parameter. Like yesterday I mentioned that in a fluid domain or within a system, what I am calling system is that the part of the model that I will actually do the simulation is my system. So, and there are some global properties of the system, and there are some integral properties of the system. Yesterday I mentioned. Do you have any idea about that? What are the global properties and what are the integral properties? Can anyone please tell me? Okay, global properties are actually the properties that is actually universal, and local properties, it actually, or the integral properties, it actually varies in different points of the system or the model. Okay, have you got my point? The global properties are actually the universal properties, and the integral properties are actually the properties that actually varies at different point to point. And then you have to perform the grid independence test. Yesterday I talked about that, so I don't want to prolong on that. And today we will actually see a real life case, and we will actually try to know the different features that we actually enable. Okay, so welcome to today's class. And yesterday we actually talked about rectangular subchannel, fuel subchannel. And today we will actually try to simulate this model. So if you have a close look at this model, what I have actually created, can you please look at this geometry and please tell that what is actually this? What I actually have created. Can you please tell anyone?
So this is a sub-channel flow.
This is a subchannel. This is a fuel subchannel of AP1000 reactor. Okay. So I'm considering a single fuel subchannel. So in this single fuel subchannel, I am just considering that the water flows freely through this subchannel. There is no baffles or special grids or anything. I didn't consider anything or any obstruction here. So what is actually my case, you can see that this is the inlet. This is the inlet. Have a very close look at this geometry, that this is the inlet and the water goes out through this. This is the outlet. And I have taken a length of 600 millimeter, and the whole subchannel length in real life scenario is 3.5 meter. So I have taken 600 millimeter. Why didn't I take 3.5 meter? Can anyone please tell?
Sir, can you
In the
please repeat? So can you please repeat your question?
Okay, my question is that if you see a commercial AP1000 reactor, in that reactor, the fuel subchannel length is 3.58 meter. But in my ANSYS, I have taken the subchannel length and this smaller length. Why didn't I take this 3.58 meter? That is the real length of a commercial reactor fuel subchannel. Can anyone please tell?
Because we works with a model, not a prototype.
Yeah, thank you. Thank you. It's a quite a good answer. And the main answer is that if you take the whole fuel subchannel, for example, in this subchannel, whenever the length is 600 millimeter, I can perform my simulation with 70,000 node. But whenever you are taking the whole subchannel, then you have to maybe to perform or to get a good result, you have to take 50 million node. So whenever you actually try to perform the simulation, I think that will be very much time consuming, and you need a good processor and very high setup to solve those kind of situation. Whenever you have got very high node or the grid, or you have got a very very robust tree. So that's the main purpose of the scaling. We actually scale it up to a smaller portion, that is the model, and then we perform the simulation. But here we also have to consider one thing, is that I have taken 600 millimeter. Why didn't I take a length less than 600 millimeter? I could have taken 100 millimeter. That would actually ease my job at a great extent. But why didn't I do that? I didn't do that because whenever the flow actually is entering through this inlet or into this subchannel, we actually need to give a certain length to the flow so that the flow develops fully. And if we actually let the flow develop fully, then we can have the real and the accurate properties of the flow or the flow dynamics. Have you got my point? I think this is a bit difficult. And if you have actually completed your fluid mechanics course, I think already you have idea about this, and but if you don't understand it right now, but when you actually go through the recording later, I think these words will actually help you at a great extent. Because if you want to model a system, there are certain things that you need to consider, and one thing is that modeling a flow, you need to have a length that is enough so that the flow develops fully. And in different operation of the ANSYS, like what operations you have to choose or step-by-step guide, you will find all these things in different tutorials. But these theoretical things you need to match with your ANSYS procedure. So you need to give a length that is enough for fully development of the flow. Okay, you can see that here I have actually marked a region of 300 millimeter. That is my entry region. That means 300 millimeter at least we have to keep for giving some floor for the flow to develop. And then after that, we have got the fully developed region. That means the flow is fully developed now. So all the properties that we need to take for the flow must be taken in the fully developed region. Go through your fluid mechanics course, or in level 4 you will perform your ANSYS course. Then you can able to relate, I think. So please just have a gesture of the few things that I'm saying, that about the grid independence, about the sets of the equations that we will solve, about the model and the prototype. Just keep these points in your mind, and then whenever you will actually delve deep into the topic, you can actually relate more. Okay, so are you getting my points, students?
Yes, sir.
Okay, so we need to give a length that is enough for the fully developed flow. Okay, so now we need to actually have some predetermined values that we will give input into our ANSYS model, so that we actually can simplify our equation. Yesterday we have seen a sets of partial differential equations. That is my continuity equation. That is the conservation of the momentum equation. The conservation of momentum equation is the famous Navier-Stokes equation. And then we saw the partial differential equation for the conservation of the energy. So let's have a clear picture that whenever you are doing the simulation of a computational fluid domain, why we have actually considered these three equations. One is the conservation or continuity equation. That means we are considering that the mass remains same within this system. And second one is that the conservation of the momentum. That means momentum also conserved within this system. And then whenever we have got any kind of heat involvement or heat applied, then we are also considering this conservation of energy. That means that energy is also conserved within this system. So this is the concept of the control volume. Control volume, I think you have learned this term in your fluid mechanics course. This is the control volume. It means the specific part of the volume of a system on which we are interested, and we are considering that the mass within the system remains constant. The momentum within the system remains constant, and the energy within the system remains constant, regardless of the operation that you perform within the system. So that means we have to apply three equations. One is the conservation of the mass, the conservation of the momentum, and the conservation of the energy. Have you got my points?
Yes, sir.
Okay, does it seem a bit difficult or understandable? You can reply to me so that I can actually get your real feedback.
So it is understandable, but needs a lots of practice, I think.
Needs a lot of practice. And what I'm trying to give you is that underlying the cause that why you perform ANSYS. Like you will do deep operations in ANSYS. Like you can go step by step, but you need to know that why I'm actually doing this. What are my approaches? I have seen the sets of equation, conservation of momentum, conservation of energy, conservation of the mass, but why I'm actually saying that conservation? Why the mass is conserved? Why the momentum is conserved here? Why the energy is conserved? Because this is control volume. So suppose I am actually considering just a fluid flow through a pipe, no heat transfer involved. In that case, we just use conservation of mass and conservation of momentum. We don't use conservation of the energy in that case. But in case of a reactor fuel subchannel, can you exclude the part heat? No, you cannot exclude this part heat because from the fuel pins, we are actually generating lots of heat, and this heat is actually transferred into the flow or the fluid that is actually passing. So we need to also consider the heat. Okay. So we also have to consider the conservation of the energy. So I don't want to prolong on that much, but I think you need to keep in this mind these things so that whenever you will actually perform ANSYS, you can actually relate. So the values that we need to know for simplifying our calculation, that is the inlet temperature. So we know the inlet temperature or the temperature of the water when entering into the fuel subchannel. The temperature of the water while entering into the fuel subchannel, that is 279.4 degrees Celsius. You can find it in IRIS, or you can find it in different papers or in any design document of AP1000 reactor. That is the operating pressure. That means the pressure that is actually maintained throughout the primary circuit. The same pressure is actually maintained within the fuel subchannel. That is the inlet velocity, the third point, the velocity at which the water is entering into the fuel subchannel. Then the wall heat flux, that means the heat flux that we are actually getting from the fuel pin. That is actually quite interesting, and you can see that the green mark portion of the fuel subchannel that is in contact with the fuel pellet. Do you agree with me?
Yes, sir.
From the previous photo, you can see that this is the fuel subchannel and these are the fuel pins, and this part is actually in contact with the fuel pin. This part, this is exposed to the another subchannel. This part, it is actually this part actually is in contact with the fuel pellet. This part, this is actually in contact with the fuel pellet. So I have marked the portions that is actually in contact with the fuel subchannel, in contact with the fuel pin with green color. So in this portion, we will have a heat flux. That means the heat that is actually producing from the fuel pin will be transferred through this phase to the subchannel. Do you agree with me?
Yes, sir.
So this is one fuel pin. This is another fuel pin. In that side, we have another fuel pin, and in this side, we have another fuel pin. Do you agree?
Yes, sir.
Student, does it seem difficult to you, students? Okay, I proceed, and I think whenever you go through the recording, you will have a better understanding. So this is the wall heat flux. That means in per meter square or unit meter square area, what is the heat flux that I'm giving? And then the Reynolds number, I have actually, we can calculate it from the parameters that is actually available with us. We can have the Reynolds number, and we have to calculate the Reynolds number. Remember, whenever you are performing any flow simulation, at first you have to calculate the Reynolds number because we need to know whether the flow is laminar or the turbulent. Our scenario will be different based on whether the flow is laminar or the turbulent. So Reynolds number is the parameter which will actually decide that whether our flow is laminar or turbulent. So it is very important that at the very outset we calculate the Reynolds number so that we can actually proceed accurately. So whether our flow is laminar or turbulent. In our case, Reynolds number is very high. So in our case, the flow is the turbulent flow. All the sub-channel that you take, it can be of different reactor. It can be any kind of small modular reactors. It can be any kind of molten salt reactor. It can be water-cooled, water-moderated reactor, or whatever you take. In most of the cases, I shouldn't say most of the cases, in all the cases, the flow is actually turbulent because in the primary circuit, we have got a very high pressure and the velocity of the flow is very high. So you cannot maintain a laminar flow within the fuel subchannel. And with laminar flow, you cannot actually increase the heat transfer rate also. So we need a turbulent flow for efficiently removing the heat from the fuel pin or the heat that is actually generating from the fuel pellets. Have you got my point?
Yes, sir.
Okay. So we actually know these parameters and then we are actually going to the boundary conditions. So boundary conditions, what I have taken that these are actually based on the experiences. Sometimes some boundary conditions may seem a bit strange to you, but eventually when you work with the boundary conditions and you will actually understand that to simplify those partial differential equations, you need to actually make assumptions quite frequently, and these assumptions are actually your boundary conditions. So the first one is the velocity inlet. That means this is a very popular term, the velocity inlet and the pressure outlet. So you have to specify the velocity of the fluid that is entering into your computational domain, and also you have to specify the pressure of the fluid or the flow that is coming out from your computational domain. So, and then hydraulically even surface, that means this smooth surface. And you can see that whenever the fluid is or the water is flowing through the sub-channel, it's actually coming in contact with this fuel sub-channel or fuel pellet wall. Whenever the fluid or the water that is actually passing through this sub-channel, it is coming in contact with this fuel pellet wall. And this wall can be rough and this wall can be smooth. So if we actually consider that this wall is rough, then our calculation will be much more complicated. And we are not even interested on the smoothness of this surface. So we actually consider that this wall that is in contact with the flow or the fluid is actually smooth. This is smooth wall. This is smooth wall. So this is also our another assumption that hydraulically even surface or the smooth surface. Then we have another boundary condition, wall surface has a constant heat flux. So these are my wall. This is the face that is actually in contact with the fuel pellet. So it has got a constant heat flux. Here we have actually considered a constant heat flux. And here the constant heat flux is 650,000 watt per meter square. You can also calculate it based on the data that is available with you. if I actually show it, it will take a lot of time and it will distract us from this ANSYS learning procedure. So just I have actually written the value that is 650,000 watt per meter square. That is the heat flux that is actually given in the face or in the wall of the fuel subchannel. So in this case, our wall surface has a constant heat flux. There are some cases that you may face that wall surface that doesn't have a constant heat flux. The heat flux is a function of sine or cosine, or wall flux is a function of tan. So that means with the varying position of the fuel subchannel or the length of the subchannel, the wall flux differs. That means whenever it's the at the entrance, the wall flux may be low, or at the outlet, whenever you are proceeding to the outlet, the wall flux can be high. So there may be condition that wall flux is not constant. You may also face this kind of situation. In that case, we have to adjust accordingly. And mixture of fluids are single phase homogeneous mixture. Obviously, we are actually considering water here. It's single phase and nothing is mixed with the water, and it's a homogeneous mixture. Fully developed, forced convection, turbulent flow. It is also a very important boundary condition. It means that we are considering that our flow is fully developed. As I mentioned earlier, that you have to give enough length to the flow so that the flow is fully developed. Without having a fully developed flow, you will not get the results accurate. So whatever you consider, it is laminar flow or the turbulent flow, you need to consider that whether the flow is fully developed or not. In laminar flow, this effect is quite negligible, but in case of turbulent flow, you cannot neglect this parameter. And we have said forced convection. That means water is actually flowing at a very high speed, so the convection is actually forced. And the turbulent flow, and on the fuel rod wall, no slip condition. Fuel rod wall that we actually want to see, this is our fuel rod, and in this wall there is no slip condition. If we actually consider slip condition, that means whenever the fluid or the water will come in contact with this pellet, it will slip. But here we are considering no slip condition. And pool boiling is not credible. There are two types of boiling. One is pool boiling, another one is flow boiling. And whenever you are actually try to boil a pot of water, we call it pool boiling. That means water is contained in a pool, and here in this case we have got flow boiling. If the water boils, it will be flow boiling, but we cannot let the water boil within the fuel subchannel. You all know that why we don't allow the water to boil within the fuel subchannel. Can you please answer? I think you know that. If the water boils, what will happen?
So water balls in fuel and fuel. Sir, please can you please repeat question?
So if the water boils within the fuel subchannel, what will happen? Is it permissible?
No, sir.
Why?
Because if water boils there, because there will be bubble will be formed, and this bubble will damage like cladding material properties.
Yeah, this can be, and it will lead to various destruction. Okay, like increasing the criticality and everything. So we cannot let the water to boil. And non-interacting subchannel, you will understand this boundary condition later. So now I will actually go to ANSYS, the ANSYS interface, so that you can have a very good understanding what we are actually doing. And so this is the main interface of the ANSYS. and when you will open, you will also see that, and you will have a lot of time to practice seeing my recording. So at first there is the geometry. I don't want to say a lot about this geometry because this is like the same interface like AutoCAD or SolidWorks, and you can just draw as it is. Here I have actually created a sub channel, a single fuel sub channel of AP1000 reactor, and you can also create it by yourself. This is not very difficult. Simple geometrical operations, step by step. I have actually created a plane. I have created this plane and then extruded it, and then I actually got this whole geometry. So this is my geometry, and it has a length of 600 millimeter. It has a length of 600 millimeters. So I have actually created this geometry, and then I will go to the meshing. There are lots of interesting things that we will learn in the mesh part. So let's have a look at this. Students, I want to take a break of 2 minutes, please. Okay, I'm in mesh, and can you see me? Hello? Hello? Can you watch the screen?
Yes, sir.
Yes, sir.
Okay. So this is the mesh. So what I have actually trying to create that while creating mesh, you have to be smart. You have to be smart so that you need to understand your work properly while creating in the creating mesh. So what are the things that we actually have created? That at first we will do the face sizing and body sizing and the edge sizing. So if you have a look at this geometry, what you will actually see that we have got a certain number of faces. So this is one face, this is one face, this is another face, and we have another face here, we have another face here. And if we actually turn back, face, this is a face. So these 2D surfaces, we are calling it face. Have you got my point?
Yes, sir.
Okay. And then we have body sizing. So what is actually body? This full geometry, we are calling it body. This whole system, we are calling it body. So this is a 3D element. Understood?
Yes, sir.
Whole geometry, we are calling it body. And after that, we have got edge. So if you have a close look at this geometry, you can see that there are some single lines. This is a single line, and this is a single line. This is a single line, and there is another single line. There is another single line. These are called the edges. Have you got my point?
Yes, sir.
So we have got 3 terms. One is face, another one is the body, another one is the edge. So in case of 3-dimensional objects, you will get these terms, but whenever you are dealing with 2-dimensional object, you will just only get the edge or the line. Whenever you will deal with 2-dimensional object, you will just deal with edge and the line. But whenever we are actually dealing with three-dimensional object, we'll consider the body, face, and the edge. Here we are dealing with what? Two-dimensional or three-dimensional?
It is.
Three-dimensional.
Three-dimensional. Okay. So what we will actually do, we will do the face sizing, and we will do the body sizing, and then we will do the edge sizing. So whenever you are doing the face sizing, you can see that whenever we are clicking on this, we have an option that is element size, type element size. You can see that element size. So we will actually select a certain value for the element size. So this element size in our case is 5 into 10 to the power minus 4, 0.0005. This is our element size. Have you got my point?
Yes, sir.
So this is the size of the one arm length of the cell or the node that we will actually produce. So if you have a look at this mesh, you can see that this is my mesh, or this is the grid that I finally generated. And if you have a close look at this grid, and if you see this is the one arm of a cell. And the thing that I mentioned, that the element size, this is actually the size of the one arm length of this cell or the node. Have you got my point?
Yes,
Yes,
sir.
sir.
So when we will want to vary the number of the node, or want to vary the number of the grid or the cells, or the number of the divisions, what I will do, I will decrease this element size, or I will make one element size, one cell size smaller. So if I make one element, one cell size small, then the total number of the cell or the grid will be increased. Do you agree?
Yes, sir.
How? Please explain.
Sir, total area is remaining same. That's why.
Okay, yeah, that's it. So if I actually make one cell or the grid small, the total number of the cell to cover the whole area will be increased. So as I said, that during grid independence test, you have to increase the number of the nodes or the cells, and have to test that whether my solution varies or not. Did I say that?
Sir, varies and more accurate.
So grid independence test, sir.
Yes, during grid independence test, we have to increase the number of the nodes or the cells, and then have to check whether my solution varies or not, right?
Yes, sir.
I said about it earlier. So how we will actually increase the number of the node? You will decrease the element size, and thus you will increase the number of the nodes or the cells. Have you got it?
Yes, sir.
So this is an approach that you can follow to vary the number of the nodes or the grids within your system. That is decreasing the element size of a single cell or the node.
Sir, I didn't get the point decreasing the element size. Sir, how can we decrease? What is the process?
Okay, you can see that right now we have total 25 lakh 34,715 nodes. Can you see that?
Yes, sir.
This is from the statistics part. Okay.
Sir,
In
what
your
is the
mesh,
meaning of element size? Length.
length. Yeah,
Oh, okay, sir.
This is the one arm length of a particular cell or node.
Okay,
This
sir.
is one arm. Okay. this
Yes,
line
sir.
length. So right now we have 25,34,715 node with element size. That means the one arm length of one single node is 0.0005. So I want to decrease it. If you decrease it, okay, I have decreased it to like previously it was 5. I want to decrease it to 48. 0.0048. So I have decreased the element size. Now I want to see that whether my node number increases or not. I have actually generated the mesh and want to see. Obviously, the node number will increase. Let me check. It's taking some time, obviously. Our today's class will be a bit long because we have got lots of things to cover afterwards. So what we actually will see that eventually our node number will actually increase. So you can, when you will actually perform that operation by yourself, you will also see that. So this is the main thing that I wanted to tell. Size, you can vary the number of the grid. So okay, the operation is complete, and then we will actually see that. Like if we go to the mesh, we will see that number of the nodes is changed. So another part is the named selection. We want to create some named selection for our geometrical body. Okay, now it's check. You can see that the node number is now 27,76,760. So have you seen that the node number is increased?
Yes, sir.
Okay. So this is quite understandable that how we actually can increase the node number. So now we are actually creating the named selection. What is this named selection part? It means that we have to give name at the different parts of this fluid domain. At first, inlet. So this is the inlet. This face is the inlet through which the water will actually enter into the fuel subchannel. And this is the entry region, water contact. This is the entry region. I have actually divided my whole geometry to two parts. One is the entry region and another one is the fully developed region. And you can see that in the entry region, we have actually named this phase as the water contact phase because this part of the fuel subchannel is not in contact with the water. And then we have fully developed water contact. After the inlet, we have got entry region. And then after this, the water, the flow becomes fully developed. So this region is the fully developed region. So this is the phase that is actually in contact with water. You can see, as we said, that this curved part, this is actually in contact with the fuel pellet. So this is the entry region. This is the fully developed region part that is in. So this is actually the named selection part. We have to define the name, that what is the purpose of the different parts. So this is my outlet. This is the outlet, and you can see this is my outlet, and this is the outlet. And if we click on the inlet, this is the inlet. So at this part of the meshing, you have to create the named selection, and then we have to generate mesh, and our mesh is created. After that, we have to go to the setup part. From here, you can see that after the mesh, we have got the setup part. And in this setup, we will actually incorporate our desired boundary conditions. This is the most important part. This is the setup part. In this setup part, we have to incorporate our desired boundary condition. So at first, we create the geometry. Then we perform the meshing. After the meshing, we have got the setup part. And in this setup part, we have to incorporate our desired boundary condition. So at first we create the geometry, then we perform the meshing, then we perform the meshing. In the meshing, we have to perform the body sizing, face sizing, and also edge sizing. Like we are specifying the element size of the mesh or the node of the body of the face and also at the edges. And then the whole geometry that is actually divided into the different meshes will be exported into the setup. In this setup part, we will actually put our boundary conditions. Okay. So right now, this is clear till now.
Yes, sir.
Does it seem difficult to you? You can please tell. Anyone, any level 1 students right now listening to me? Or any level 2 students? You can just say hi to me. No need to answer any questions or anything. Okay. Any level 3 students?
Yes, sir.
Okay. And level 4?
Yes, sir.
Okay. Level 4 students, have you gone through your CFD course yet or
Sir, CFD course is ongoing.
is ongoing? So what do you have learned so far from there? Like
Sir,
what are the topics? Can you
1D and 2D heat transfer problem, heat flux problem.
Okay. So we are actually dealing with the same things. And I think this course has become a bit advanced for all of you guys, but eventually this will help you. Not like right now, maybe after 6 months or after 1 year or maybe after your graduation, this course will help. Afghanistan match, right?
Yes, sir.
Maybe the World Cup. Okay. So now I will dig into the setup part. This is the most interesting and intriguing part of ANSYS. And if you open the interface, this will be like this. Like in you will perform all the operations in this left-hand box. In this left-hand box, you will perform all the operations. So you can see that okay. So in this left-hand side, this is actually kind of a tree. Like if you click on this plus signs, the whole option will actually come or the branch of the tree will be open. If you click on this plus sign, the branch of the tree will open. So at first I would like to go to the model. So if you click on this model, the multi-phase option, it is off because we are dealing with a single phase or multi-phase. Please reply.
Single phase.
Single phase, very good. So multi-phase option will be off. Energy equation will be on because here we are dealing with energy. There is heat transfer involved. I said earlier. Did I say?
Yes,
Yes,
sir.
sir.
Yes. Then we have got viscous flow. Obviously, this is a viscous flow. We need to consider the viscosity of the fluid. So this is also on. Radiation off. Does we have any involvement of radiation? We are not considering here. We are only interested in the flow and the heat transfer characteristics. We are not interested in radiation. Okay. Do you get
Yes,
my
sir.
point?
But
Yes,
sir,
sir.
ignoring the radiation,
Here we are not considering the radiation because this radiation, ionizing radiation will not actually affect the flow parameters or the heat transfer parameters right now. And in this radiation option, you have got another thing. This is the radiative heat transfer. As far as I know, that the heat transfer can be of 3 types. One is the conduction, convection, another one is the radiation type. That means when the heat transfer actually moves as a wave. So this is also an option to actually incorporate here, but we are not actually considering this. And another one is the heat exchanger. We are not considering heat exchanger here. And another one, the species, this is quite advanced. The discrete phase, this one is advanced. Solidification and melting, nothing is melted here or nothing is solidified. Acoustics, we are not considering the effect of sounds. And Eulerian wall film, we are also not considering this. What we are actually considering this, and if you actually keep to the basic fuel sub-channel calculations, you have to consider these things, this energy and this viscous flow. So if you double click on the viscous point, you can see that there are different models to actually solve this viscous flow. There are different models. If you look that this is in viscid, if you actually put tick mark on that, it will actually say that in our case we are not considering the viscosity. If you don't consider the viscosity of the fluid, then you have to choose this inviscid option. If your flow is laminar, in our case the flow is laminar or turbulent? Turbulent flow. So we will actually ignore this laminar, and then we have got all other options. I will not actually go one by one because this will take lots of time, and we actually deal with in our undergrad level with these two types of equations, that is k epsilon or k omega. K epsilon or k omega, these are actually modeling. That means you are actually following this approach to solve your equations. So if I first talk about the k epsilon model, solves the transport equation for the turbulent kinetic energy. K epsilon, it actually solves the equation for the turbulent kinetic energy. K omega, this is also same, but it gives us a more improved result. So we will, between this k epsilon model or k omega model, we will actually choose the k omega model. And in this k omega model, there are also three types of subsets, that is standard, BSL and SST. So if you choose the SST model, that is the k omega SST model, then this k omega SST model, this is a combination of k epsilon and k omega model. So you will have more better result. K epsilon, this is quite good. This will give you solution very easily, but the result will be less accurate. K omega, it will give you improved result. But if you choose k omega SST, which is a combination of k of epsilon and k omega, it will give you the best output. So we have chosen k omega and the SST model. Okay. After that, we have to choose. What about BSL?
Yes, sir.
If you choose BSL, this will also give you a good result, but this is not as good as the SST model. SST model, this is the shear stress model. This is the shear stress model. And if you choose the BSL model, it will actually have got some constraints, and it will actually it doesn't consider the shear stress fully. So we actually prefer this k omega SST model rather than k omega BSL model. Have anyone used k omega BSL model previously?
No, sir.
Okay. So okay, this BSL model, this is actually stands for the baseline model. Okay, baseline model. So SST model is the shear stress model. So we actually don't, this is quite basic. So this will not give you the right approximation. Like I also worked with this BSL model, but didn't get good output. But in SST model, I actually got good output. Okay, then after that, the material. That means the fluid that will actually flow through the sub-channel. In our case, this is water liquid. So if you actually have a click on this material, this will pop up. Fluid, air, solid, aluminum. You just click on water liquid and you need to define the properties of the water here. The density of the water, the specific heat of the water, thermal conductivity of the water, and the viscosity of the water. These are the fundamental properties that you need to assign for the flowing fluid. What is the density of the water?
So normally 1000 kg per
1000
meter.
kg per meter cube, but in your fuel sub-channel, the temperature is not atmospheric temperature or the pressure, right?
Yes, sir.
The temperature is quite high. The pressure is quite high. So you need to consider the properties of the fluid at this elevated temperature and pressure. Like density, specific heat, thermal conductivity, and viscosity, all needs to be counted in that and the pressure. The temperature that is actually maintained in the fuel sub-channel. Do you understand?
Yes, sir.
Because do these properties varies with temperature and pressure?
Sir,
This,
can you repeat your question, sir, again?
This density, the specific heat, the thermal conductivity and viscosity, all these properties, does it vary with temperature and pressure?
Yes, sir.
Or is there any property that doesn't vary with temperature and pressure? No, all these four values or the four parameters, they vary with pressure and the
Temperature.
temperature. And we have also fluent database. The ANSYS, they have also database where you can actually choose the flow, fluid, acetone, acetyl chloride, air, aluminum arsenide. They have actually have a rich
ভাই
database of.
ভাই I have a question.
হ্যাঁ, ওকে বলো শামীম। হ্যাঁ।
ভাই ভাই যে প্রপার্টিজ গুলা অ্যাকচুয়ালি হচ্ছে দেখেছেন, এই প্রপার্টিজ গুলোর যে ইকুয়েশনস গুলো আছে এগুলা স্টুডেন্টরা কোন বই থেকে পাবে, বা এই এটা একটু যদি বলে দিতেন আর কি। যে ইকুয়েশন গুলো তো
আচ্ছা
সলভ করে তারপরে ভ্যালু গুলো বসাতে হয়, তো এই ইকুয়েশনস গুলো কোন বইতে আছে একটু যদি রেফার করে দিতেন।
আচ্ছা আচ্ছা আচ্ছা, শিওর। ওকে, so for standard values, you will actually get these standard values in any kind of STM table or ASME steam table. ASME steam table, American Society of Mechanical Engineers. They actually have a steam table that is actually quite popular, and in that steam table you will actually find their ideal properties. But for these properties at elevated temperature and pressure, you need to actually go through some certain graphs. There is a website that is Engineering Toolbox, and in that website, Engineering Toolbox, they actually provide a graph where they have actually shown the properties. Like in x-axis they have varied the temperature, in y-axis they have varied the thermal conductivity, or in x-axis they have put the pressure, and y-axis they have put the viscosity. And from that graph you have to actually calculate that at that elevated temperature and pressure, how we can actually calculate these parameters. And if you, this is a very easiest solution that I have said, but for more specific and more accurate values, you have to go to some research papers. And on AP 1000 there are some research papers, and in those papers some people have actually clearly mentioned that these values at AP 1000 operating condition. So can you download any research? Do you know the process how to download papers from the internet? I think level 4 students can already know it. Okay, maybe we will learn it in another session. So so this is the property that we have actually specified, and then we have got the boundary conditions. This is the most important part, like the boundary conditions. So we will go one by one. So we have seen that in the mesh part we have a very specific section, that is the named selection. We have actually given name to the different parts of our geometry. Have we seen that? In the mesh portion, we have actually a certain part where we have given name to the different portion of our geometry. Have you seen that? Can you remember?
Yes, sir.
Okay. So this whole thing will actually appear in the setup. So at first we go one by one. In our computational domain, at first we have the inlet. So double click on inlet. You will see that in the inlet, we had a velocity of 4.50. Have you seen it?
Yes, sir.
Like we in our slide, we have seen that. I want to show you that in our slide. In a slide, we had a velocity, inlet velocity of 4.5 meter per second. We know that value. So in this boundary condition, we will actually put this portion. Okay. 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 So this is the portion where we actually will set the inlet velocity. So you can see that if you double click on that in inlet, then you have at first the option that is the momentum, and here you have to put the value velocity magnitude, and that is constant. The inlet at the velocity is constant, the velocity magnitude. So whenever you have to, in most of the cases, you have to put this value, that is the velocity magnitude in the inlet. So you put the value here. Okay. And then we have got the outlet, pressure outlet. We said the velocity inlet and the pressure outlet. In our case, the pressure at the outlet, we have actually taken 0. We are considering that this one is actually open to the atmosphere, though in real case this is not. It is open to the atmosphere, the pressure in the outlet will be 0. This assumption will help us to simplify our equations a lot, but this may seem strange, but still this is needed to actually accurately simplify our equation. So velocity inlet, pressure outlet, velocity inlet, pressure outlet. Velocity at the inlet is 4.50 and pressure at the outlet is 0. Then what we have got else? We also have a constant heat flux at the wall. Constant heat flux at the wall. Can you remember?
Yes, sir.
Okay, so at the constant heat flux at the wall, we have got entry region wall. You can see the entry region pellet contact wall. at the entry region, we have actually said that we have divided the whole domain into two parts. One is the entry region, another one is the fully developed region. So in the entry region, there are some four walls that is in contact with the wall, right?
Yes, sir.
That is in contact with the pellet part, fuel pellet. So this is the entry region pellet contact wall. You can see if we go, here is one option, that is shear condition, that is no slip. As we have said that there is no slip condition. So we will actually enable this option. And if you go to the thermal, there is option heat flux, and we have actually given this heat flux of 650,000, and we have actually kept it constant. As I said that this heat flux can also be not constant, it can vary along the length of the fuel subchannel, and then you don't keep this constant, you just select this option, new input parameter, and then you have to define it. But in our case, the heat flux is constant, so we have actually selected this portion. Okay. So in the wall that is actually not in contact with the fuel pellet, that is actually exposed to the adjacent subchannel, in that case heat flux is 0. So we have actually taken heat flux 0 there. So these are the boundary conditions that we have actually put it. And after that, this is the reference value. This reference value is the initial gauge. Initial gauge that we, as we have said that in your ANSYS, after creating geometry, putting mesh, and then taking it into the setup, applying the boundary condition, then you have to put some initial gauges, like from where the computational process will actually start. So compute from the inlet, as our computational domain starts from the inlet. Here we have seen that in inlet we have got an inlet velocity, as it starts from the inlet. So we will select this option that compute from the inlet. And this is the area. This is the frontal area of the inlet face. This is the frontal area of the inlet face. And this is the density of the fluid. This is the enthalpy of the fluid at that pressure and the temperature. This is the length. So remember, this is very important, and most of the students, they actually make mistakes in this case. Whenever you are selecting this reference value and it comes to the length, in your subsequent work, when you will work with fuel subchannel or any heat exchanger or any flow through the pipe, if you work with the steam generator, if you work with any kind of heat exchanger, and when you model this, and you have to put the reference value and you have to specify the length, this length is not the whole length of the computational domain. This is the hydraulic diameter. This is the hydraulic diameter of the control volume. It can be heat exchanger, it can be any kind of pipe, or it can be fuel subchannel. This length, this is the hydraulic diameter. So don't actually set a value. Pressure is 15.51 megapascal. This is the operating pressure of, so here I have actually put the value in the pascal. This 15.51 megapascal, this is the operating pressure. This is the temperature at the inlet. This is the velocity at the inlet. This is the viscosity of the fluid. And this is the ratio of the specific heats, Cp by Cv, that is 1.4. Specific heat at the constant pressure and specific heat at the constant volume. Then we'll go to the solution method. This solution method is a simple skip. Yes, please.
Sir, is the defined area for one mesh?
No. This is the area of the whole frontal face. Are you talking about this area?
Yes, sir.
Okay, this area is, let me show you. This is the area of this frontal face. You can see this is the face.
Okay,
This is
sir.
the inlet face or outlet face, we have got the same area. This is the area of this frontal face. Okay, as we have actually computing from the inlet, so this is the area of this inlet face, this blue portion. Have you got
Okay,
it?
sir. Yes, sir.
Okay, okay. So then the solution method, this is the solution method that we will actually follow. It takes a lot of time actually to elaborate this portion, but what is most important that for this pressure velocity coupling, remember, whenever we are putting a boundary condition which involves velocity inlet, that means at the inlet of the computational fluid domain, we specify the velocity, and the pressure outlet, that means at the outlet, we specify the pressure. Then we have to do this pressure velocity coupling. And for do that, we actually choose this simple scheme because this is actually less hassle. It involves less hassle and it actually saves our time a lot. So we have to choose this simple scheme, and then these are the spatial discretization that actually we actually put them in second order. All the equations we actually set them in second order, and then we have got the solution control, and this is the place. These values are actually automatically set by the ANSYS, but one trick that I want to teach you is that whenever after doing all this you learn you run your solution or you run your simulation, it may seem that your solution will not converge sometimes, and then at that time you can vary this energy value. Like this energy value can be varied from 0.6 to 1, and if you place that you have set a value of energy 0.9 and you are seeing that your value is not converging, solution is not converging, then you can actually set this value to 0.8, or if you see that it's not still converging, then 0.7, or if you find that your solution is not actually going to the ideal one, not going close to the ideal one, then you can also value this energy value. Then you set it to 0.6. So from 0.6 to 1, you can set any value and actually adjust your simulation. So, but other values, you don't need to change that. The pressure, density, body forces, these are the default values set by the ANSYS. Then another next thing, that is the monitor. That is the monitorial parameter. That is actually here. One thing is actually important, that we will go to the residual. What is actually the residual? This is very important, that what is the residual value that you select. And you can see that what we actually here solving. One is the continuity equation, x velocity, y velocity, z velocity, then the energy equation, conservation of the energy, and the k and the omega. So these are the equations that we will actually solve. And what is the meaning of this residual? Please listen carefully. In ANSYS, when they actually do the simulation, they actually perform lots of iterations. That means, what is actually an iteration? In your numerical method course, I think you have learned about this, that we actually select an initial guess, and that based on that initial guess, we proceed to solve the equations, then we get a result. And if we see that close to the ideal one, we take another initial guess, and this is the actually procedure of iteration. So this will this residual value that you set, set here, that 0.0001 or 0.0001, this is actually the difference between two consecutive iterations solution. Suppose after doing 500 iteration, I have got a value of 76, and in the next iteration, 501 number iteration, I have got a value of 77, then ANSYS will not accept it because you have put a residual value of 0.0001. If you see that after performing 500 iteration, your value is 76, suppose the value of Nusselt number is 76, and after doing a iteration of next iteration, 501 number iteration, your residual value is, if your Nusselt number value is 76.0001, then ANSYS will accept it. That means the difference between two consecutive iteration, the acceptable difference, iteration solution. Did you get my point? Does it seem difficult, or did you get my point?
Yes, sir.
Can you explain? Okay. So you can also search for what is actually the meaning of residual in case of numerical iteration. You can search for this and you will also easily understand that. But the smaller that you choose the value of the residual, the more accurate will be your solution. So remember, this residual is the difference between the acceptable difference between the solution of the two iteration. Remember this one definition, then things will be very much clear to you. So we have to solve these values, and we cannot actually keep this below 0.01 or 0.001. This 0.0001, this is the standard value for the residual, and the smaller that you choose the residual value, the accurate will be your solution, but it will be very much time consuming. Then solution initialization. We have got two types of initialization: hybrid initialization and standard initialization. For turbulent flow and complex geometries, we actually use hybrid initialization. Here you perform this initialize. It will be initialized, and then after the initialization, when you actually click this run calculation option, and then our calculation will be started. Now I am just letting it to initialize. It will take 10 iteration to initialize, and in the run calculation portion, you can actually set the number of the iterations that you want to perform. You can perform 100 iteration, you can perform 200 iteration or 500 iterations, but your iterations number should actually be sufficient enough so that your solution converges. If your solution doesn't converge, then I think you have to increase the number of the iterations in your solution. So remember, before performing or running your calculation, you have to initialize your solution. You can see that here we are actually initializing our solution. It's initialized. You can see 7, and then up to 10 iterations, it will actually perform its initialization. And we will not actually run the simulation here because it will take a lot of time. But we will actually then see the post-processing or the result. It's saying that hybrid initialization is done. So it's complete. Now we'll go to the run calculation. You can see that number of the iterations. You can actually select it here. I have actually 500 iteration I have selected. You can also decrease it, or you can set the value to 200 iterations. And then if you click this calculate option, it will start the simulation. Now we'll go to the post processing. If you go to our main portion, you can see that the geometry we have covered, we have got mesh, we have covered setup, the solution part, how we solve, and then if you click the result after the simulation, we will actually get an interface like this. So here we actually do some post processing. There are lots of options, but I'd like to show you one. That is the velocity profile that we want to see. So here we have got some certain options. One is the very simplest and the very most popular approach that I want to show you is that here in this interface you have got an option that is location. That means in this point you can actually create any point or any point cloud, any line, any plane, any volume, any isosurface, isoclip, or any user surface or any polyline in your computational domain. You can create any point, line, or plane in your computational domain. So in this case, what we will actually do, we will create a plane here in our computational domain. So we have actually created a plane here, and you can see this is a plane. This plane 4 is actually created, and we can actually select the specific area where this plane will be created. Let me actually select what this plane will be created. Okay, so this plane 4, we want to see the velocity profile of the flow throughout this computational domain. The velocity profile of the flow through this computational domain. So my inlet, this is my outlet, this is the outlet, and this is the inlet. This is the inlet. This is the inlet of my computational domain. This is the inlet, and this is the outlet of my computational domain. This is the outlet. So the flow will actually enter through this region, and then it will actually go out through this. So I want to see the velocity profile, how we actually achieve the fully developed flow. I want to see that. In the velocity profile, there will be a certain, do you know that how about the D shape velocity profile, the capital D shape velocity profile of a flow or the fully developed flow? Do you know that? Anyone have any idea about that?
Yes, sir.
Yes, sir.
Okay. Okay. So we will want to see that here in this ANSYS. So we will actually select a plane. If we actually select a plane that actually cuts this fluid domain into half, then we can see the velocity profile here. So we will actually create this plane, and we want to set the value of close to 6.3. It will help us 6.3 millimeter. And it would be YZ plane. Okay, so here we have created a plane that is cuts the fluid domain into two halves. So here you can see that, can you see the axis here? This is the x-axis This is the y-axis and this is the z-axis. Can you see?
Yes, sir.
So if we want this plane to cut off this fluid domain, or the plane is in this direction, if I actually draw the plane in xy plane, then it will not happen. It will not actually serve our purpose, because our plane, this has to lie along this direction. So we have to draw this plane in YZ surface, in YZ plane, right? Do you understand me? In YZ plane, I have to draw this plane, not XZ or not XY. Do you get me?
No, sir.
You can see here clearly. Understandable? Okay. Oh, you can see that this plane that we have actually created, this ash color or the gray color plane, this is in the YZ plane. You will understand it eventually when you work with it. So our main purpose is that to create this plane, and after creating this plane, we want to select another portion that is actually contour. We want to see a contour, create a contour, and in that contour we want to see the velocity profile, or we can actually select this contour 1, and then we have actually created a new plane, that is plane 4. We want to see the velocity here. We can actually see different kind of thing, different contours through this plane. That can be density, that can be eddy viscosity, inner wall temperature, pressure. But here we want to see the velocity. So then we apply, and we want to see the result. It's taking time. We want to see the velocity profile throughout this fluid domain. At the entry region, we will have some D-shaped profile, and at the okay, so our profile is actually created, and this is the outlet, and this is the inlet region. And in inlet region, you can see that we have got some D-shaped velocity profile. Can you see that?
Yes, sir.
So this is the D-shaped velocity profile, and this is quite stiffer at the very beginning. And as the flow actually moves, it becomes more roundish, and after the fully developed flow, it actually diminishes. So have you got it?
Yes, sir.
So you will actually learn this post-processing by yourself when you work on with this. But very important thing that I want to say, that at first you have to set a location on your computational domain. It can be any kind of point, it can be any kind of plane, or it can be any kind of line. And then you have to select a contour, and in that contour, what property you want to see, you have to select. This is the most basic and easiest way to post-process your data. Just remember these things, and whenever you will work with this will actually help you. So far this is my class, and if you have any question or anything, you can ask from this today's schedule. This is difficult actually to fathom, I think, this huge volume of task, but you can still ask any question or any recommendation or anything that you want from me. You can feel free to please feel free to ask me.
Sir, I think it will better if you have show me the modeling process of the cylinder pipe in ANSYS.
Modeling process of
pipe, that pipe. Which you have demonstrated. Yes, modeling process of that pipe in ANSYS.
how can we model this kind of 5-bit ANSYS?
Okay, okay, okay. That would be much easier, you are saying.
Yes, sir.
Okay, I could have shown that, but I actually tried to give you a real picture. Like, as you are from nuclear engineering background, so I wanted to actually give you the real gist of a fuel sub-channel. But it was quite complex because lots of things are involved here. Okay, maybe in the next class or maybe in the next sessions, I will try to give you a simple geometry with which you can actually practice. I will give you that practice material there. But I strongly suggest you that you listen to this recording whenever you actually deal with your projects or your thesis or any further work future. You can also use these words that I have said as a reference, because this will help you for basic understanding of your theory, why you are using ANSYS, why you are actually giving certain boundary conditions, and why you are actually setting some reference values initial cases. I think this is for your core understanding, and eventually I believe that your skill with ANSYS will increase when you practice with it, and software is something that someone will not be able to give you full understanding. Software is something that you yourself have to go through this, like different nook and corners, different options. Yeah, if I do that, what will happen? But what I think I tried to do that to enlighten you, or to that why you are doing this, rather than how you should do this. Okay, so I think I tried to do that. Maybe I think this will help you. If you have any suggestion or feedback, you can tell me, or any question that you want to pursue. Okay, so I think we can conclude. So thank you all for your kind participation, and I appreciate you very much. And I wish you all best of luck in your future endeavor, in whichever path you go. But always try to remember that whenever you are dealing with any software, please try to know the basic and the fundamental theory that is lying underneath this software. And also, I wish you all best of luck. And it was a good session for 2 days. Thank you very much. And if you can remember quite a few words from my course, that is actually my achievement. And I think this is the success.